We had been looking at the equivalent circuit of the transformer in the last class, and I said that we are going to look at the performance parameters of the transformer in terms of its voltage regulation and efficiency. So let me redraw the equivalent circuit of the transformer, what we discussed yesterday. So this is the voltage that we are applying on the primary side, and this is the resistance, which is the winding resistance of the primary side, and this is going to be the leakage reactance, that is representing the amount of leakage flux that is actually visualized from the primary side. And from here I'm going to have two components which are in parallel. One is going to be representing the core loss component. The other one is going to be the magnetizing component of the reactance. Now these two are connected on the primary side in parallel with the voltage source, and you are going to have the secondary side resistance and leakage reactance. Both of them actually are transferred to the primary side, so we call this as R2 dash and we call this as X2 dash, and we are going to connect the load here, and the load is ZL dash. So this is going to be ZL dash. So we are going to say that R2 dash will be equal to the actual winding resistance on the secondary side multiplied by N1 divided by N2 the whole square. So this R2 is the winding resistance of the secondary side, and N1 by N2 whole square is the turns ratio. So X2 dash, the same way we wrote that as X2, whatever is the original leakage reactance of the secondary side multiplied by N1 divided by N2 the whole square. I have just reiterated whatever we did in the last class in terms of the equivalent circuit of the transformer. Now we said that this current, what is flowing through the no load branch, that is, let us say this is IM and this is IC, and the summation of these two I called as I0, and I called this current as I2 dash, and when we added I2 dash and I0 together, this was I1, right? So just to reiterate, I0 equal to IM plus IC, and I'm going to have I2 dash plus I0. That is going to give me what is I1, right? So now, if I say that I0 is normally less than 5% of rated value of I1, in that case, we can say for all practice, so this is the current that is carried here. So I can neglect this for all practical purposes if I am not unduly worried about efficiency. So I can write sometimes the transformer equivalent circuit is drawn as though I'm going to have R1, then I can have R2 dash, and I can have X1 and X2 dash. And I'm going to just have V2 dash coming up here. Okay. So this is approximate equivalent circuit of the transformer. This is an approximation. So this is an approximate equivalent circuit of the transformer, where I'm neglecting the parallel branches. The parallel branches are generally not neglected if I'm calculating efficiency, because RC is going to play a role in decreasing the efficiency. It is going to actually have some losses. So if I don't care so much about efficiency right now, efficiency calculation right now, then because the current drawn here is really small, I can afford to say that I1 is approximately equal to I2 dash, which essentially tells me the parallel branch current is neglected. So if I neglect the parallel branch current, I can simply remove this and I am drawing this as the approximate equivalent circuit. And what is done is this R1 and R2 dash together, it is called as R equivalent. This is the equivalent resistance of the transformer inclusive of the primary and secondary winding. And this is known as the equivalent leakage reactance of the transformer, which is including the primary as well as secondary winding leakage reactances. So I can draw simply from here as a very simplified form of equivalent circuit as R equivalent and X equivalent. And I'm drawing this from the primary side. I can definitely draw the same thing from the secondary side as well, in which case I can say R equivalent equal to X1 dash plus X2 if I'm trying to look at it from the secondary side. Okay, so here I can show again the load being connected, which is connected in the form of ZL dash, and the voltage across this is going to be V2 dash. So this is going to be my output voltage, which is V2 dash. This is one of the simplified forms of equivalent circuit of the transformer in this particular case. So if I really want to know the performance of the transformer completely, I should know the values of RC, XM, R equivalent and X equivalent, because in all probability I may not be able to segregate R1 from R2 dash and X1 from X2 dash. I may get only the total resistance and total leakage reactance. So these are generally known as the parameters, or I should say equivalent circuit parameters. Okay, equivalent circuit parameters of the transformer. So these are the major 4 equivalent circuit parameters of the transformer, which first of all need to be determined if I want to know the performance characteristics of the transformer. So this is essentially leading us to how to determine the equivalent circuit parameters. So let us try to look at determination of equivalent circuit parameters of the transformer, after which we look at the performance of the transformer. Okay, so determination of equivalent circuit parameters of the transformer. So let's try to take a look at how we are going to determine the equivalent circuit parameters of a transformer. So as I told you, these are the 4 things that we are going to determine. And when I am not having any load connected on the secondary side, I'm not going to have any current flowing through this at all. The secondary branch will be open circuited, so there will not be any current. If there is no secondary current, there is no reflected current from the secondary side onto the primary side. So there is only no load current that is going to be drawn by the transformer. Nothing else is going to be drawn by the transformer. So if I want to know what is the kind of core losses incurred in the transformer, what is the kind of magnetizing current is drawn by the transformer, then the easiest way to do that is to keep the secondary on open circuit. So the first and foremost test normally we do on any transformer, if I want to determine the parameters, is open circuit test, or it is also called as no load test. So this is the first test normally we will perform in any transformer. So whenever we are talking about a very large transformer that is generally used in a power station, let us say I have a 500 MVA generator. Along with the 500 MVA generator, there will be a 500 MVA transformer because it has to transport all the power to the transmission line and eventually it will reach the customers or consumers. So you are normally going to see extremely large rated transformers being employed in power stations, many of the power stations. So if I am really looking at the test, in all probability, I will not be able to load the transformer fully to 500 MVA. Then I have to really have massive resistances, massive reactances, which will be able to dissipate so much of power, 500 megawatts of power. And it is a wastage of power. So that is the reason why we try to determine the parameter of the transformer without really loading it. We are not going to load it completely. We are doing something like a phantom loading. What we mean by phantom loading is we may apply rated voltage, but the current drawn will be very minimal. Or we may apply or we may draw rated current, but the voltage will be very minimal. So voltage multiplied by current is the overall power. So if I really look at the transformer and say that minimum current, but rated voltage. Okay, so I'm going to have minimum current, but I'm going to apply rated voltage. In that case, again, V multiplied by I, that will be really small in this particular case. But you will be testing the transformer for rated voltage condition. If it is rated voltage and rated frequency, it is rated flux, right? So if it is rated flux, the core losses will be at rated value. Okay, so you are looking at open circuit test, something like minimum current and rated voltage. The other test which we will be doing eventually, which we call as short circuit test. The short circuit test actually will be maximum current or rated current and minimum voltage. So we are going to have this particular test, that is short circuit test, conducted at rated current but minimum voltage. So in both cases, the power consumption is going to be minimal. You are not going to see a very high power consumption at all. Power consumption is going to be low. That is the reason why we call normally these tests as phantom loading tests. We are really not going to load the transformer actually, but it is creating a situation as though either the voltage is at rated value or the current is at rated value. So that is the way it is going to work normally. Okay. So this is the kind of crux of determining the parameters of the transformer. So let us look at open circuit test first and then eventually go over to short circuit test. So let me first of all take up open circuit test of a transformer. So what is done in an open circuit test is we are going to actually apply, let us say this is the primary of the transformer and we are going to have the secondary here. The secondary is on open circuit condition. Okay, I'm not going to apply any load or anything. It is just left open. Under this condition, I'm going to apply rated voltage. So this voltage is going to be rated voltage. So when I apply rated voltage, I can check what is the kind of current that is being. So I am applying rated voltage here. I'm going to measure what is the kind of current that is actually being drawn by the transformer. So this is an ammeter. Please remember it is an AC ammeter. We are talking about AC, so there is no plus minus. Absolutely. Okay. And You are going to connect the wattmeter also so that you would be able to get exactly what is the amount of power that is being consumed by the transformer at no load condition. When there is no load, the load is not consuming any power. So the only power consumed is because of the core losses. Because the current drawn is very small. So if I try to look at the current, what is the current drawn here? That is going to be no load current. And no load current is generally less than 5% of I1 rated. I'm talking about this from the primary side. That's the reason I'm writing I1. So it is going to be less than 5% of rated current. So even if I try to look at what is I1 square R1, this is going to be generally whatever is 0.05 whole square multiplied by I rated square, right? This is going to be the actual current square multiplied by R1. So you would see that it is 0.0025. It's a very, very small, minuscule percentage of what is the normal copper losses you may see, I square R losses you may see in the primary winding. So it is negligible. So that is the reason. So this becomes negligibly small. This is negligible. So that is the reason why, this is why the wattmeter reading, what you get, you may call this as W0 because it is open circuit test. That's why W0 indicates primarily the core losses. Whatever is the hysteresis loss and eddy current loss, that is indicated now by W0. W0 is really, if you look at it, it will have I square R losses also from the primary winding, but that is negligibly small. That is the reason why we take it as though the W0 value is only equivalent to the core losses of the transformer. Okay. So this is going to be core losses now. So this W0 what I have is core losses, and I can put a voltmeter here between the two terminals of the primary winding, which will measure V0. So I would be able to get basically V0, I0 and W0. These are the readings of the no load test or open circuit test. So the open circuit test of the transformer is going to give majorly three readings. One is V0, the voltage input to the transformer, which should be adjusted to rated voltage. So I should adjust it to rated value of voltage. So this should be generally rated value. Whereas what I get as I0, that will be no load current. And W0, generally what I get will be core losses. These are the three readings I'm going to get. Now, if I have these readings during the no load condition, because we are neglecting the series components completely, we have the no load equivalent circuit somewhat like this. We are not going to have R1 and X1 because they are primarily not going to play any role. So I'm going to simply have only RC and XM. And I'm going to have this open circuit. This is what is the equivalent circuit of the transformer under open circuit condition. So I'm going to have this as V1, and I'm going to have, I can call this as V0 now because this is no load condition. I'm calling this as V0, and I'm going to have this as I0, and this is going to be IC, what is flowing here, and what is flowing here will be IN. I should be able to segregate these two because I can say V0, I0 cos phi naught will be equal to W0. This should be valid no matter what. And I0 is drawn here. So V0, I0 cos phi naught is W0, from which I should be able to calculate the no load power factor, which is cos phi naught. That can be calculated as W0 divided by V naught, I naught. Okay. Now when we drew the phasor diagram, if you may recall, we said that if this is V naught, along with V naught in phase with that, we had IC. And we had the other component of current as IM, the magnetizing current. And when we added these two, we got I naught. This is what we drew as the no load conditions phasor diagram. So this is going to be, now if I look at what is IC, I can call this angle what I have got between V naught and I naught as cos phi naught. This is going to be cos phi naught, or that is the angle phi naught, sorry. This is the angle phi naught. So I can say I naught multiplied by cos phi naught will be IC. I naught multiplied by sin phi naught will be IM. So from here I should be able to calculate as I naught multiplied by cos phi naught is IC, and I naught multiplied by sin phi naught is IM. So I should be able to write this as V naught divided by IC, or I naught cos phi naught, is going to give me RC, which is the fictitious resistance, which is equivalent to representing the core losses. So the core loss component can be easily represented by this RC. Similarly, I can write V naught divided by I naught sin phi naught will give me XM. So I would be able to determine both XM and RC as well as core losses from the no load test or open circuit test of the transformer. Okay. So whenever I want to determine the equivalent circuit parameters, which are parallel components in the equivalent circuit, for that I have to do it with open circuit test or no load test, where I'll be applying rated voltage to the transformer's primary winding or secondary winding as the case may be, and I would leave the other winding on open circuit. If I am applying the voltage on the secondary side, I leave the primary on open circuit. If I am applying the voltage on the primary side, I leave the secondary on open circuit. Which side will I apply the voltage? That depends upon which is your low voltage winding or which is your high voltage winding. So if I say that this is going to be my low voltage winding, I would prefer to always, apply the lower voltage rather than the higher voltage. If I say that I'm going to have 100 by 200 volts, I will definitely have 100 volt source as well as 200 volt source. It's quite easy to find these sources. Whereas if I'm talking about a power station where I'm going to have a 500 MVA transformer with, let us say, 15 kilovolts slash 1500 kilovolts, for example. It is not going to be easy for me to find a 1500 kilovolt source, which is the rated voltage of the transformer if I look at it from the secondary side or higher voltage side. So 15 kilovolt source will be easier for me to find rather than 1500 kilovolt source. So open circuit test will always be conducted from the low voltage side because it is easier to find low voltage sources pragmatically rather than very high voltage sources. 1500 kilovolt source will not be available very easily anywhere. Okay, so that's the reason why generally you see that open circuit test will be conducted from the LV side. From the LV side, low voltage side, you will try to apply the voltage. You will try to connect the wattmeter. You will try to connect the ammeter. The high voltage side, you will leave it on open circuit. So that is the way normally open circuit test is conducted. So from open circuit test, we get mainly three things: RC, XM, and the no load losses. That is core losses. That's what we get. Okay. Now let us look at the second test, which is known as short circuit test. So the short circuit test, on the other hand, just like the name indicates, I'm going to have one side of the transformer applied with some voltage, current and so on, and the other side is going to be short circuited. So one side of the transformer is short circuited. So this is the short circuit, and I'm going to actually have the other side applied with voltage and current and so on. But we told that the transformer will have very low leakage because we are having iron core, and the resistance will also be very small. It will be low because it is thick copper coil. So obviously, if I apply 400 volts and simply short circuit the whole thing, the current is going to be enormously high. If I try to short circuit, it is as good as short circuiting line and neutral, which is deadly actually. You will see immediately the fuse will blow. So you can't apply normally rated voltage. So what you are going to do is to apply a reduced voltage. You will apply a reduced voltage. To apply a reduced voltage, I can use a potential divider. That is one of the easiest things. But the potential divider will also have huge amount of I square R losses. So that is why we use something called auto transformer. An auto transformer is simply like one single coil. Let's say I have a core like this, and I'm going to wind a huge number of turns around this. Okay, and I'm going to apply, let us say 100 volts here, and let's say there are 100 turns here. If I take the output from this point until, let us say 25 turns, then I'll get 25 volts. If I take the output at 50 turns, please understand, in a transformer, voltage per turn is a constant depending upon what is the amount of flux established. So as the number of turns increases from the tapping point, I am definitely going to have more and more voltage output coming up. So this is going to be, if I call this total number of turns as N, and if I call that this number of turns as N1, I'm going to have N1 divided by N multiplied by 100 volts. That is what is going to come up as the output. And as I told you, the leakage reactance is small, the resistance is small for a winding which is wound around the core. So there will not be much of I square R losses, nothing much. So compared to a potential divider does the same function. There is no doubt. But the potential divider is basically made up of a resistance. I'm going to have a huge resistance. This resistance is going to have, let us say, the same 100 volts applied. Now I'm going to take some portion of the output here. Obviously, I square R losses will be quite high here. Whereas here I will not have much of losses at all. So normally what we try to do in this kind of test is, we will use an auto transformer. So let me show an auto transformer like this. This is an auto transformer, and I'm going to apply rated voltage V1, whatever here, and I will essentially adjust the voltage as per my requirement by having a variable terminal. Okay, so I will have an ammeter here, of course, and this ammeter you have to constantly watch. As you increase the voltage slowly, you have to watch this ammeter such that it does not exceed the rated current. If you are given, let us say 2.2 kVA, 220 volts divided by 110 volts transformer for testing, then you know that the primary side current is 10 ampere. I1 rated will be 10 ampere. 2200 divided by 220. That will be 10 ampere. Secondary side will be 20 ampere. So if I am connecting the voltage source on the primary side, which is the high voltage side, I am essentially going to watch this ammeter until it reaches 10 ampere of current. The moment it reaches 10 ampere, I should stop my variation at that point. I should keep the voltage at that point. And I should see how much is the voltage that is available here. I have to read the voltage here. Okay. So this is going to be 10 ampere and I have to read exactly what the voltage is by putting a voltmeter here. So I would say here what I get is VSC, ISC, and of course I'll put a wattmeter. So I can also imagine I'll put a wattmeter here. So let me probably erase this and put a wattmeter along with an ammeter also. So I'm going to have an ammeter here and a wattmeter here. Okay. So I have a wattmeter reading, I have an ammeter reading, I have a voltmeter reading. So I can write this as VSC, ISC and WSC. As I told you, the resistance is very small. The leakage is also very small in a transformer. So there is no other impedance that is restricting the current here. So only impedance what is restricting the current. If I try to again look at the equivalent circuit under transformer short circuit condition, I'm going to have R1 plus R2 dash as the total resistance and X1 plus X2 dash as the total reactance. And what I am doing is applying here VSC. I will not show this as V1 because if I apply V1, you will see immediately a big fire hazard. So you cannot apply rated voltage under short circuit condition. Extremely large current will flow. If the fuse is there, fuse will blow. If not, you will see the entire transformer burning. It's deadly, really deadly to apply rated voltage. So you will normally apply much reduced voltage and you would see that this side is short circuited. Now what you are supplying here is I1 rated. So I'm going to have VSC equal to I rated multiplied by R1 plus R2 dash plus J times X1 plus X2 dash. This is going to be my short circuit voltage. So I should be able to write this as I rated multiplied by R equivalent plus J X equivalent. X equivalent consists of both X1 and X2 dash and R equivalent consists of both R1 and R2 dash. Now what we get from here will be very clearly I rated square multiplied by R equivalent is going to be WSC. What I get as the wattmeter reading has to be only dissipated in the resistance. Obviously, reactance will not play any role in dissipation. So the power loss incurred by the transformer under this particular condition, I am taking it as what is dissipated in R equivalent. But why not? Why not? I mean, why are we not considering the core losses under this condition? Because core loss should also take place. After all, it is electromagnetic induction which is happening between the primary and secondary. Then there should be established flux. Then why are we not considering that? That we'll have to check. Okay. So why are we neglecting core losses? Neglecting core losses under short circuit condition. Unless we satisfactorily answer this question, we can't afford to neglect the core losses. That's what I'm trying to get at. Okay. What we are applying as the voltage is only VSC. And we said that these are very small. This is also very small. How small is small? That's another question we'll have to answer. So normally what we will see is this will be only about 1 to 2% of the total voltage drop. Whatever is the voltage drop that is taking place in the resistance will be about 1 to 2% of the rated voltage. And in the leakage reactance, what is taking place as a drop will be only about 3 to 4%. Nothing more than that. This is a thumb rule I'm talking about. Nobody deliberately designs a bad transformer. Nobody wants to waste their voltage or power in a transformer. It's meant for stepping up or stepping down, not for dissipating the power. So generally you would see that VSC will be less than 5% of rated voltage. Most of the times this is how the good transformers are designed. Just like how you say no load current is only 5% of rated current, the short circuit voltage will be only 5% or less than 5% of rated voltage. If I am applying only 5% of rated voltage, you recall the equation what we wrote. V equal to 4.44 F5 multiplied by the number of turns. From which we can say flux is proportional to voltage divided by frequency. So voltage divided by frequency is going to be equal to flux. So the flux is equal to voltage divided by frequency. So if the voltage is only 0.05 times V rated, frequency is at rated value, then I'm going to have essentially flux is 5% of rated flux or less than 5% of rated flux. The core losses are heavily dependent upon what is the flux value, right? So I'm going to have the core losses which are proportional to about 5 power 1.8 or 5 power 2. So this is going to be only 0.0025 times rated core losses. Okay, so this is going to be something like this. It's not going to be any higher than this. And that is the reason we can say core losses can be neglected under short circuit condition. So that is why we are neglecting core losses under short circuit condition. So let us look at the calculation corresponding to the short circuit test. Yeah. Calculations. So the calculations corresponding to short circuit test we can write as WSC equal to VSC multiplied by ISC multiplied by cos phi SC. We have WSC with us, VSC with us, ISC with us. So we can get what is cos phi SC. So I can say cos phi SC equal to WSC divided by VSC, ISC. So cos phi SC if we determine, now I can write, we are having the impedance VSC divided by ISC is going to be ZSC, right? The impedance during short circuit condition, which is consisting of R equivalent plus J X equivalent. So I should be able to calculate R equivalent as ZSC times cos phi SC and X equivalent as ZSC times sin phi SC. Okay. So we would be able to get this as R1 plus R2 dash. It's difficult to segregate R1 and R2 dash. So normally what we do is R1 equal to R equivalent by 2, which is also equal to R2 dash. That's how we assume. This is an assumption. The same way we are going to say this is equal to x1 plus x2 dash. So x1 equal to x2 dash equal to x equivalent by 2. Okay, got it? So short circuit test actually allows us to determine the series parameters. Of the transformer equivalent circuit. Open circuit test allows us to determine the shunt parameters of the equivalent circuit, whereas the series parameters of the equivalent circuit are determined by the short circuit test. So the short circuit test and open circuit test allows us to determine specifically the series and shunt parameters of the equivalent circuit, apart from determining the copper losses and the core losses. We call I square R losses as the copper losses because it is dissipated in the copper conductor. Core losses are dissipated in the core of the transformer, so we call them as core losses and copper losses specifically. Okay. Now that we have the losses determined, we have the parameters of the equivalent circuit determined, we should be able to assess the performance of the transformer. Rather, performance assessment. Performance assessment of the transformer. So how are we going to really assess the performance of the transformer? If we look at it, two performance parameters specifically we see for the transformer are efficiency. The second one is voltage regulation. What we mean by voltage regulation is, if I apply, let us say, the rated voltage V1 here, and I look at what is available at the load terminal, whether exactly, let us say if I have a voltage ratio, for example, again 220 by 110 volts, I'm taking the same transformer repeatedly. Okay. So if I'm taking a 2.2 kVA 220 by 110 volts transformer, if I apply 220 volts here, I should get 110 volts here. Normal. But there will be some drop within the transformer because I am having R equivalent and X equivalent, no matter what. So it is going to definitely drop some voltage. The drop in the voltage depends upon how much is the current I am drawing. How much is the current I am drawing? If I am drawing rated current, maybe the drop will be couple of volts. If I am drawing only less amount of current, then maybe the drop will be less than that. So how much the output voltage is varying? So the voltage variation, how much is the voltage regulated or it is controlled? How much I am able to really maintain the voltage at 110 volts, irrespective of the load condition, right? That is generally called as voltage regulation. So voltage regulation referred to what it is referred to, what is the internal drop within the transformer. And efficiency basically refers to if I apply whatever is the kVA or kilowatt from the input side. So what is the input kilowatt versus output kilowatt? If most of the kilowatt is consumed by the transformer itself, it's a useless transformer. It should pass on whatever it is taking to the output side clearly. If it is consuming a lot of it inside, then it is not of any use. Okay, so these two are extremely important performance parameters of the transformer because we don't want a lot of voltage to be dropped within the transformer. We don't want a lot of power to be consumed by the transformer itself. It should be able to pass it on to the load. The load we represent by generally some resistance or inductance or capacitance or whatever. But in actual practice, if you look at it, all our domestic appliances, all of them are loads for the transformer. All the industrial appliances, let us say we have a printing press, tire making industry, cement mill, paper mill, whatever, all of them are consuming electricity from the distribution system. And all of them are connected ultimately through all the transmission lines, distribution lines to the generator through a transformer, right? So we are going to have the loads what we see in the power system, whether it is domestic, whether it is commercial. Commercial means I'm talking about a mall, maybe many shops, cluster of shops, or it is a residential complex, maybe it is an industry, maybe it is a metro rail. Everything is a load on the transformer ultimately. Okay, we are just representing that by some ZL, which is a load. That's it. Okay, so the current that is drawn from the transformer is going to be enormously high. I hope you understand, because if it's a 500 MVA generator, right, and ultimately it is supplying power at 1 kilovolt or something, it's going to really take 500,000 of ampere, right? So it's going to be extremely hundreds of thousands of amperes of current will be drawn by the transformer ultimately. So you are looking at a very huge current flowing here. That's why even if the current, the resistance is 0.01 ohm, 0.001 ohm, you can imagine if it is multiplied by 500,000 amperes of current, it's going to be enormously high in terms of voltage drop. So that is the reason why we would like to have this R equivalent as well as X equivalent as low as possible. So that's the reason why we normally use very good quality copper for the transformer conductors, and we tend to reduce the leakage as much as possible by having different types of applications, whatever we talked about, to reduce the leakage reactance. So we tend to reduce it as much as possible. So when we start with efficiency, we will call efficiency in general as output power in watts or kilowatts, whatever, divided by input power in watts again. We will not talk about this in terms of kVA. We will talk about this in terms of kilowatts or watts. Definitely not in terms of kVA. So what we would say is output kVA multiplied by power factor. We have to multiply this by power factor. And similarly divided by input kVA if we talk about as kVA. Rather than that, we would say output kV kilowatts plus losses. What losses take place in the transformer under this particular load condition? We have to add those losses. So this is going to be the efficiency expression, which we can write. If I am writing it from the secondary side, I should write V2 I2 cos phi 2. Cos phi 2 is the angle, or I can write this as cos phi L also. That's fine. Load power factor. Because ZL will have a power factor which is corresponding to cos phi L. Divided by, I will have V2 I2 cos phi L plus I will have P iron losses. I'm writing that as P iron, and I'm going to have copper losses. These are the major two losses in a transformer. There is no moving part, so there is no mechanical loss. Any rotating electrical machine will have some mechanical losses as well. Friction losses will be there. But here I will have only this much. So we will start from efficiency in the next class. When we are actually looking at our next lecture class, we'll start with efficiency.